Welcome back to Learning with the Fosters, and welcome back to El Caribe, or the Caribbean, or Caribbean. Mars just gave a great lesson on definite singular articles based on whether they're feminine or masculine, so I'm really into trying to get those right. For instance, our cat Snowflake is a male, so tell me if I get this right. He's a male, even though gato is the same word. It would be gato, ends in O, he'd be el gato, because Snowflake is a male cat. Woody is a female, so she's a cute little gata, so it'd be la gata. All right,
Very good.
got that straight. So now let's go to our math. We're going over our homework today based on our lesson where we talked about intervals. Intervals on the real number line. And in that discussion, we also had to look at or review some basic inequalities. So our task was to look at each of these statements, these inequalities. Remember, an inequality, again, to reiterate, is a statement involving one of these symbols: less than, greater than, less than or equal to, greater than or equal to. So we want to see if these are true statements or false statements. That's our goal. So negative 23.7 is greater than negative 22.8. Well, that looks right. 23 is greater than 22. But wait, these are negatives, remember? If we look at our number line, negatives, if 0 is our origin, our negatives grow, negative 1, negative 2, negative 3, or decrease in quantity the farther one gets moving leftward on the real number line. So negative 22.8, if this were that point, the negative 23.7 would be more in the left direction. It is less than negative 22.8. So this is not a true statement, is it? Saying negative 23.7 is greater than negative 22.8? No, it's not. It's false. All right, how about 12 over 4 is less than or equal to 3? Well, we've got this rational number here. Let's see if we can simplify that to help us be able to gauge its relation to 3. So 12 over 4, we can simplify this, right? In fact, we can divide both the numerator and the denominator by 4. 12 divided by 4 is 3. 4 divided by 4 is 1. So 12 over 4 is just another way of writing 3. So we're essentially asking, is 3 less than or equal to 3? Well, 3 is not less than 3, but it is equal to 3. So while this may not be an overly helpful statement, it may be more helpful to say 12 over 4 is equal to 3. It is not a false statement. We can say it is a true statement because of it allows for the two quantities to be equal. In this case, they are. This is just another way to write 3. So this is a true statement. Negative 12 is less than 0 over 6. Okay, another rational number. Let's look at this. So it's not, we don't have 0 as the denominator, so we're okay. It's defined. Remember, you can never divide by 0, but you can certainly take 0 and divide it by another number, another real number. In this case, the integer 6. So what is 0 divided by 6? Well, it's 0. So is negative 12 less than 0? Again, perhaps maybe not as, perhaps it's a little counterintuitive because we think of 12 as being larger than 0, but negative 12 is less than 0. If you owe somebody $0, you're square, you're even. If you owe them 12, that's negative. You owe them money, and that is less money in your pocket than having 0. So negative 12 is less than 0. That is a true statement. All right, how about 2.5, another rational number, is greater than or equal to 2.5 repeated. Remember our repeating bar, or 2.555555555. Well, these are very close, aren't they? But which one is greater? If we were to expand the decimals, we have 2.5, remember, and 2.5 repeated. The first, the 10th spot are the same, they're equivalent. But we move into the 100th spot. Here we have 0 hundredths, which is why we can simply write as 2.5. Here we have 5 hundredths, making 2.55. We could expand these as far as we wish. Repeated slightly greater than 2.5. So 2.5 is, first of all, not equal to 2.5 repeated, but it is, or excuse me, 2.5 repeated is greater than 2.5. So this is not a true statement. 2.5 is less than 2.5 repeated. And again, we saw that by working our way into the decimal spots. The 10th spot was equivalent. Moving to the hundredths, 0 is less than 5. So 2.5 repeated is greater than 2.5. All right. An inequality with 3 different numbers. So in order for this to be a true statement, we're not interested in partly true or quasi-true. All of these relations will have to be true to make this a true statement. So let's first look at, is 6 less than 19 over 3? Well, again, 19 over 3. Let's see if we can convert that to a simplified fraction or a decimal. Doesn't look like we can simplify it too much, but what we can do is we can convert it to a decimal form. Or we could do a mixed number as well, but we'll just do a decimal. So one way to read this is 19 divided by 3. How many times does 3 go into 19? Well, 6 without going over. 18. 1 remainder. Need a decimal. 3 goes into 10. 3 times. 9. 1. We see that this is going to be a repeating aspect, so 6.3 repeated. Now, this is similar to our one we looked at up here. Is 6.3 repeated, which is 19 over 3, greater than 6? Yes, it is. So this portion is true. 6 is less than 6.3 repeated, or 19 over 3. In fact, we could convert this to 6 and 1/3 as a mixed number. And 6 and 1/3, you have 1/3 extra of whatever your whole is, as opposed to just 6. If you're looking at pizzas, this would be 6 pizzas. This would be 6 pizzas and 1/3 of a 7th. So this portion, at least of the inequality, is correct. 6 is less than 19/3, or 19 over 3. What about 19 over 3 with respect to 6.3 repeated? Is that less than or equal to? Well, interesting. We converted it to a decimal, and we found that this is 6.3 repeated. So it's not less than, but it is equal to. So because this inequality involves the or equal to, this is also a true statement. 6 is less than 19 over 3, which is equal to, so less than or equal to, 6.3 repeated. So this one also is a true statement. We could write this as equals. So that works. Just to highlight, if it was simply less than, then that would be wrong. It's not less than, it's equal to. But where this was less than or equal to, this is a true statement. All right, how about this one? -2 is less than or equal to -4. Ooh. No, remember, if this is our number line, if this is 0, let's count backwards using integers. -1, -2, -3, -4. -2 is to the right of -4. -2 is greater than -4. So right away, this portion is not true. This is false. But just for practice sake, let's check out the second relation. Is -4 less than -10? Well, again, -5 up to -10. -4 is greater than -10. So this is wrong again. So this statement is not true. It is false. -2 is in fact greater than -4, and -4 is in fact greater than -10. Muy bien. We've been reading numbers, variables, and symbols and kind of translating them into English. Now let's take some kind of English phrases and translate them into numbers, variables, and inequalities. So 10 is greater than y. Our job was to write that as an inequality. 10 is greater than y. Well, whatever y is, 10 is greater than that. So a way we could express that in not so many words, which is always nice, is 10 is greater than y. Nice little easy one. How about k is less than or equal to negative, or not, excuse me, not negative, the square root of 15. So k is less than the square root of 15. Oh wait, what's my mistake here? I missed some of this information. We have k is less than the square root of 15, but we forgot the or equal to. So this is not correct. We would have to use the less than or equal to symbol. All right, d is less than e and greater than f. All right, so we've got three of these. We have to get all the relations right to make a true statement. So d is less than e and greater than f. So let's just start with d is less than e. How could we write that? Well, we could write that as d is less than, we're used to that, e, now, and greater than f. Well, what is greater than f? D. D is less than e, and d is greater than f. So d is less than e, but d is greater than f. So let's read this kind of as we have it. We were saying that f is less than d. That makes sense because d is greater than f. We're saying that d is less than e. That's spelled out fairly explicitly here. So we're good. F is less than d, which is less than e. There's another way of writing d is less than e and greater than f. M is less than the natural numbers. Well, what are the natural numbers? The natural numbers are 1, 2, 3, 4, 5, etc. So we want to say that m is, I guess we could just write it this way. M is less than the natural numbers. But let's write it another way involving the least of the natural numbers, since we're dealing with m is less than all the natural numbers. So the least natural number is 1. So we could say m is less than 1. So every number up to really close to 1, but not including 1, m is less than. Now we don't want to say less than or equal to, do we? Because that would say that one of the natural numbers is equal to m, but that's not what this is saying. This is saying m is less than all the natural numbers, the least of the natural numbers being 1. So we could write it either of these two ways. M is less than fonted n, or m is less than 1. And on a number line, that will give us the same picture either way. M is all of the real numbers less than 1, but not quite up equal to 1. The next job, we've got 4 different inequalities. Remember, these are intervals are sets of numbers, so these are a way to describe the set. We could say that this set is the set of all elements x such that x is, and here's our definition of these inequalities. So our job is to take these inequalities, and it is then twofold. To graph them, we've got some number lines started, we must graph them, and also write them in interval notation. So let's do the interval notation first. So we have negative 3 is less than x, which is less than or equal to 2. So we want to describe the interval of all elements x. So we have, in this case, we have 2 endpoints. We have negative 3 and 2. X is in between those. So this interval will include all the real numbers between negative 3 and 2. Remember how we write this. But what's really important is that we pay attention to our inequalities to correctly put in either parentheses for an open interval or brackets for the closed interval. Remember, the parentheses for an open interval include all the points between the numbers, but not the endpoint, not that last number itself. The brackets do include those. So in this case, negative 3 is less than x. So x does not include negative 3 because x is greater than negative 3. So we would use this end of our interval is open. All the real numbers between negative 3, but not including negative 3 itself. Negative 3 is not an element in the set. So x is between negative 3, but not including negative 3, and it is less than or equal to 2, so it goes up to 2. Does it include 2? Well, yes. This less than or equal sign says that x can be equal to 2, therefore including 2. So we want to use the bracket for around the 2. So here is our interval notation for this inequality. This interval consists of all of the real numbers, all the points on the real number line between negative 3 and 2, not including negative 3, but including 2. Well, we pretty much summarized it. It shouldn't be too hard to graph at this point. We have negative 3 and 2. Are we including negative 3? No. So remember how we denote that an open circle. 2 we are including, so a filled-in circle, which is just how we've been graphing points on lines prior to this. And this interval includes all of the points corresponding to all of the real numbers in between negative 3 and 2. Again, not including negative 3, but including 2. Let's look at the second one. 21 is less than x, which is less than 100 over 4. Or in other words, x is between 21 and 100 over 4. Well, let's first of all look, what's a simpler way to write 100 over 4? 100 divided by 4 is 25. So that simplifies things a little bit, although we could leave it in this unsimplified form, but this will just help us see this, and it's a little bit cleaner, a little bit neater than 100 over 4, a little more finished. So x is between 21 and 25. Does the set of all elements x include 21? No, because x is greater than 21 and is not equal to. So parenthesis, and x is less than 25, or 100 over 4. So does the set of all elements x include 25? No, it doesn't, because then x would not be less than 25. So we've got a parenthesis on that end as well. So let's graph this. We've got 21 and 25. We're dealing with all the points in between, but not including both endpoints in this case, not including 21 and not including 25. So we use open circles. And the red, again, is denoting all of the elements in these sets, in these intervals, all the real numbers. All numbers between 21 and 25, but excluding 21 and excluding 25. Let's look at this one. This one looks a little bit simpler. X is greater than or equal to negative 6. So this interval will be the set consisting of all elements x that are greater than or equal to negative 6. So this one I think it may be helpful if we graph it first. We're only dealing with one specific point, negative 6. And we're dealing with greater than or equal to, so we can fill in the circle. So our set at least includes the real number, the point negative 6, but our set of x includes all x's that are greater than or equal to. So all of any point x will correspond to a real number that make up this interval described by this inequality, where x is greater than or equal to negative 6, including negative 6. So remember, this will go on infinitely far in the positive direction. So do you remember how we denote that? We're using the same interval notation where we have negative 6 included, so we use the square, the bracket. But what's our other number? Where's kind of our other endpoint? Well, it's not a number. We're saying that this goes out infinitely far. So we use this symbol denoting infinity. And again, this is not a number. This is not the number infinity. This is saying that all the points going out infinitely far, extending infinitely far, in this case, in the positive direction. So what do we use? A parenthesis or a bracket? Well, we can't use a bracket because that would suggest that we include that number, that endpoint. We just said that infinity was not a number, so we have to use the parenthesis because we're not stopping at the number infinity. That's not what this is saying. So we can't say something is equal to that. But here's our interval, the set of all elements x, where x is greater than or equal to -6. All right, let's look at this one. We have no numbers in this at all, just the variables. So m is less than or equal to x, which is less than or equal to j. So no big deal. And we're saying that x is in between, essentially, m and j. And look, they're both including the endpoints, as we have less than or equal to in both instances. So we have m, we have j, x, where the interval consists of all elements x in between m and j, including m and j, because of these. So square bracket m, comma, j, our interval notation. How would we graph that? Well, we've got m and we've got j. We are including those endpoints because we're allowing them to be equal to, and all the points in between. And again, so if we chose any arbitrary element x, let's say here, it should be, this x should be greater than m. It is. And it should be, or greater than or equal to m. It is. It should be less than or equal to j. And it is. So you can test that, make sure your picture matches. Very good job. Now, we are given an interval in terms of interval notation, and our job is our challenge is to describe that in terms of an inequality. We're describing a set using inequalities, and then also to graph it. So let's start with the graphing this time. Here's our intervals and interval notation. Let's first graph it. You can see the rain is starting to fall. It's good kind of extreme math weather. We're just going to keep going. So here's our interval. We have the interval, an open interval from -infinity, closed at 4. So on our number line, if we were to graph this interval is representing all of the points from a -infinity. Remember, that's not a number, but infinitely far in the negative direction, all of the points coming this way until, where does it stop? Well, at 4. Say this is 4. So what do? Do we use the open circle now or the closed circle? Well, we're including 4, so it's the closed circle. And again, remember, if we're including the endpoint, it is a closed, a filled-in circle. If we are excluding it, an open interval, it is an open circle. So here's our graph. Now let's describe, so we've described this interval in terms of interval notation as a graph or geometrically. Now let's describe it as an inequality, or the set of all elements x such that x fits somewhere in using inequalities. So if we were to use this, we'll work from our graph now. Any arbitrary point x in the interval, or in other words, everything red, could be described as how? Well, we could say x is, anywhere we go here, what's the thing that we notice? It's less than 4. Here, less than 4. Here, less than 4. What about right on 4? Yeah, that's included too. So we could say x is less than or equal to 4. So the set of all elements x such that x is less than or equal to 4 is the interval described. And again, geometrically, this corresponds to a ray on our real number line. Next one, we have an open interval from 6 to 11. So we're getting somewhat familiar with these, I think, by now, that we can kind of look on our line, on our number line. We're going to know this is a line segment, but notice it's open. It's not including the endpoints, not including 6, not including 11. So if this is 6, this is 11, we are not including those endpoints. So again, we use an open circle, not filled in, and our interval consists of every real number or every point on the line in between. What a beautiful little picture. Now let's describe it as an inequality. Well, any arbitrary x within the red, what do we notice? With respect to 6, x is greater than 6, whether we go here, 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 or here. So we can say that x is greater than 6, or we can say 6 is less than x, right? So if we say 6 is less than x, Anywhere we go, that is a true statement within the red. Now, not less than or equal to, because 6 is not included. Well, how about with respect to 11, the other endpoint? Well, anywhere we choose within the red, x is less than 11. And again, not equal to 11 is not included. Now, you may have noticed by now that when we write these, we typically tend to use the less than or equal to. And that's just kind of convention. We do that for a number of reasons that I don't think we'll probably talk about right now. But typically, we describe things in terms of moving from less to greater. So in other words, moving from left to right, something is less than something is less than something. But remember, we can use these as equivalent statements. We're saying the same thing if we say 6 is less than x, or if we say x is greater than 6. We're saying the same thing, just with kind of a flipping of with respect to. But I think it is worth pointing out that generally, and you probably noticed this, generally we state things in terms of less than or equal to, but that's no mean a goal, it's nothing that you have to stick by. It's just kind of helpful for reasons that's a little bit beyond what we're dealing with right now. But that's kind of why we state it this way. All right, next interval. The interval is a closed interval all the way around from -9 to 0. So this is going to be the line segment from -9 to 0 on our real number line. So -9, 0. We are including -9 and 0 because of the brackets. So we will fill those circles in, or those points. Remember, each real number is corresponding to a point on the real number line. And this interval consists of all the numbers, all the points, all the elements of the set in between. Nice little picture of our interval. So how could we describe that using inequalities? Well, x is with respect to -9. All the x's are greater than. So in other words, -9 is less than x. And x is, no matter where we pick, less than 0. Wait, did we make a mistake? Damaris is nodding her head. Very good. This isn't quite what we're saying. It's close, but we're missing 2 elements. Remember, we're including 9 and we're including 0. So we have to say that -9 is less than or equal to x, and x is less than or equal to 0. All right, our next one. We have the interval 5 to 8, in which this end is open and this end is closed. So my penmanship's kind of slanting, so we'll try to even this out a little bit. So 5 to -8. So this interval starting at 5, and we're not including 5, so open, we have no endpoint, so to speak, so we have a ray. So this interval consists of all the numbers, all the points from 5 on, not including 5, that extend infinitely far in the positive direction. So we can keep going. It's going to be red as far out as we go. So a similar picture to our first one, only this was extending in the negative direction. Okay, let's write our inequality. Well, we can say that no matter what arbitrary point x we choose, it is greater than 5, right? So we can say that x is greater than 5, and it's not equal to, so x is greater than 5, or we could say 5 is less than x. Ready to move on. But wait, I hope you caught this on your homework. There's a problem we haven't dealt with here yet. This indicates a closed interval, so we need some sort of filled in circle, some sort of greater than or equal to or less than or equal to symbol here. Where does that occur? Well, it doesn't, because there is no point over here. So this is really not a valid interval. This really isn't saying anything. Remember, infinity is not a number, so we can't include not a number. It's describing, in this case, kind of a process that continues on and on. So this, I hope you caught, is really not a properly written interval. We really can't write a proper picture. We really can't describe it in terms of inequalities because there's an error. This right here. When we're dealing with infinity, with these intervals, that's not a number, so we cannot include it with a closed interval. That's a big X. That doesn't work. So very good job if you notice that. All right, let's move on to the next one. First thing to notice, our infinity has an open, so we're good that way. So let's look at this actual interval. Well, here we have P. Remember, we're dealing with points and numbers. They're corresponding to each other. So wherever P is, whatever point P is, we'll just say this is P. We are including P in our interval. So a filled in circle. And any element X that we choose extending into infinity, and we're okay with infinity this time because we're leaving it open. Remember, infinity is not a number we're dealing with here. Any one we choose, here, 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 will be with respect to P, what? Less than P or greater than P? Greater than. It's always in the positive direction. So P is less than or equal to X. Or we could just as easily write X is greater than or equal to P. Okay? One more to go. Ooh, this one will be short. Take a moment to look at it before we get going if you haven't worked through it yourself yet. What do we notice? Similar problem as to up here. Negative infinity, just like positive infinity, when we're dealing with these intervals, this is not a number. So we can't have the closed notation. That doesn't make sense of what we're saying. We can't include the last number because this isn't a number. It goes on infinitely far in the negative direction. So we can't really properly denote any of these because this is not a properly denoted interval. Good job if you caught those two. Let's keep practicing. Let's move on to the next task. Now we're given intervals in terms of a graph or in terms of geometrically presenting these. Again, our job is to take this interval and describe it in interval notation and also describe it using inequalities or as a set. So this first one, let's, what do you say? Let's do interval notation first. So we see that 1 point, -1, will this be included, this element, -1, will this be included in our interval? No, the big open circle tells us that. So it's all the numbers, all the points up to -1, but not including -1. So we use the parentheses as opposed to the brackets. And this interval goes from -1 all the way to pi. Remember the irrational number pi that we'll have a lot of fun with in this course. Does it include pi? Well, pi is so important, of course we have to include pi. So we'll close it at pi. We'll include pi, so we use the bracket. Here is our interval and interval notation, all the numbers, all the points, from -1, not including -1, through up to pi, including pi. All right, let's write this in terms of inequalities. Well, any element x, which will be in red, would be described with respect to -1, greater than -1, not equal to. So -1 will be less than x, or x will be greater than -1, again not including -1, and x will be with respect to pi less than or equal to, or pi is greater than or equal to x. So this describes, or we could say x is in between -1 and pi, because x is greater than -1 and is less than or equal to pi. Excluding 1, including pi. All right, our next one. So we've got an interval that extends all the way, geometrically like a ray, into infinitely far in the negative direction. So negative infinity. Now what choice shall we use up here? I hope after our last kind of portion of the homework, and I've really been stressing this, that we know by now it is not the bracket, because this is not a number. Not a number. Speaking of infinity in terms of numbers, or the idea of numbers, our understanding of number has to expand much beyond the real numbers to really be able to appropriately talk about things like that. So I'm really trying to drive this home. So negative infinity will be an open interval enclosure. So all the way from negative infinity to 0, and not including 0, have an open interval open circle. So we have a total open interval negative infinity to 0. Let's write it in terms of inequalities. Any arbitrary element x in the red will be with respect to 0. This side, which is less than, so 0 is greater than, so we can say that x is less than 0, or we could say 0 is greater than x. And again, not equal to, because we are not including 0 on this. So any x you choose will be less than 0. All right, our next one, we have another interval where it's like a ray geometrically extending this time in the positive infinite direction, extending infinitely onwards. So our point from this end is -3, and we are including -3, a filled-in circle, so that is an element of our set, the set of all elements x. We want to include that, so we use the bracket. That's a really poorly drawn bracket. All right, and we don't have any other point to stop at. It goes on and on and on, infinitely far in the positive direction. So use our infinity symbol, and of course, again, with this, we must use the parenthesis. All right, in terms of inequalities, x, any red point or any arbitrary x we choose that is within this interval, within this set, will be with respect to -3 greater than or equal to -3. So x is greater than or equal to -3. Or again, we could say -3 is less than or equal to x. One more. Here we have the interval from -10 to 10. So -10 to 10 with respect to -10, a closed circle, so that is included, that is an element. If we labeled this interval I, we could say -10 is an element of I. How about +10? No, we're not including +10. This interval, this set does not include +10, so we use the parentheses. So we could say that 10 is not an element of I. All right, let's write it as inequalities. Any arbitrary x describing this interval will be what? Greater than -10, and greater than or equal to -10, and less than 10. So again, we could write x with respect to -10. We would say that -10 is less than or equal to x, and x is less than 10. All right, let's move on to our next task. So remember, intervals geometrically are segments or rays of the real number line. They're also sets of numbers. We're describing the sets of numbers between here and here, or here to infinity, etc. We're describing the elements of x such that x is whatever. So these intervals are sets of numbers, just like the real numbers. The real number line is a set of numbers. So when we're working with sets, oftentimes it's helpful to do this, to use the set operations that we talked about a few lectures before. So now we're going to look at these sets and perform some of the set operations. Again, the ones that we looked at were the intersection of two sets, the union of two sets, and the complement of a set. So we're going to do that now with intervals, and our job is to take each of these described situations and represent it graphically, and to also write it in terms of interval notation, I believe. Let me check the homework. In terms of interval notation. Yeah. Okay, couldn't remember exactly what we're doing there. So let's start with the graphical part. Here we have the interval, open interval 2, 7. We're going to take the intersection of this interval, we'll put this as the purple interval, and this as the orange interval. We want to find the intersection, or in other words, the elements that are common to both. And then we want to express that graphically and in interval notation. So let's first look at each of these individually and graph it on the same number line as we did in our lesson. So let's look at the purple interval from 2 to 7. It's open. If this is 2, we're not including 2, an open circle. If this is 7, we're not including 7, but this set, remember we're thinking in terms of sets really here, or this interval, includes all of the numbers between 2 and 7 in purple. Well, let's graph this set, this interval. So 3, about right here, and -3, this isn't necessarily to scale, but here's our endpoint, and we are including -3 within this set, within this interval, and we are including 3. So these circles are filled in. So what this is asking us is which, I gotta fill in the orange part, excuse me, getting ahead of myself. What the intersection between these two sets, these two intervals. Well, we see that, or let's think back to kind of how we describe these using Venn diagrams. Remember when we were looking at the intersection, the picture that it kind of looks like with our good old-fashioned Venn diagrams, if this was the purple set and this was the orange set, where they overlap, this is where the shared elements exist. Any element in here will be both in the purple set and in the orange set. So this area represents the intersection of those two sets. Well, this number line, we see a similar picture. If this interval extended to look circular like our Venn diagram, and this orange one, if we did the same thing, we notice that our middle area exists right here. And so on our number line, this includes, if we could magnify this and kind of clean this up, we'll put it down on this one underneath, our set that, remember, it has to be contained within both. So we have 2 and we have 3 representing the boundaries of our intersection, or the elements shared in common. Any arbitrary x within this region would be both within the purple interval and within the orange. Anything outside of here is unique to the orange. Anything out here is unique to the purple. And anything beyond those is not in either interval. So we're interested in this area here. So the interval between 2 and 3, I'm going to space this out a little bit just for clarity's sake. So here's the question. Remember, in order for the intersection, the element has to be in both sets. So is 2 in this interval? Should we color it in, or should it be open? Well, it's clearly in the orange set, the orange interval, but it's not included, it's excluded in the purple, right? So 2, the common area, the intersection includes all the numbers up to 2, but not 2 itself. That must remain open. Well, how about 3? Yes, that's definitely included within the orange and clearly included within the purple. So 3 is included. So our final interval picture, I guess I should be using red like I've been using. That's why I didn't have any white chalk up here. Losing my mind. So our interval looks something like this. So this is the intersection between the open interval 2 to 7 and the closed interval -3 to 3. Here's our final graphical picture. So this scenario describes, just to say this again, this describes all of the numbers, all of the points in between 2 and 3, including 3, but excluding, not including 2. So here's our graph. Let's write this now in terms of interval notation. Well, this is pretty easy. If we've been following so far our previous homework problems on here, we see that the interval is open. 2, not including 2, we're using the parentheses, and it goes to 3. We are including 3. So there we go. I don't believe we were required to do this. I don't think I had this on the homework, but if we were to write this as an inequality, we could say that 2 is less than x, and x is less than or equal to 3. There we go. All right, let's move on to our next one. We'll do the same approach. We'll look graphically first and then move to interval notation. So here we have another intersection. We're looking for the points in common. So let's use a similar approach as we used up here. Let's graph both of these initially. on this first number line. Hello, Archimedes. This is our highly educated cat, Archimedes. He's going to help us out with this one. All right, so this interval represents all of the numbers from 4, including 4, onward infinitely far in the positive direction. So if this is 4, and if this continuing onwards, we would include 4. So we'll have a filled in circle, and this interval goes on forever in the positive infinite direction. There's our purple interval. Well, let's graph our second one. This interval begins at 0, not including 0. Notice it's open, so an open circle, not including 0, and it contains all the numbers from 0 to 10 and including 10. So if this is 10, we'll have a filled in circle because we are including this within the purple interval. So this interval consists of all of these numbers, including 10, excluding 0. So the intersection, again, would include the elements that are common to both. Or color-wise, this is for you, Damaris, color theory. I don't know what the name for a purple and orange color combination is. Is that a secondary or tertiary or anything? Yeah, I'll leave that to the artist to talk about. But in our case, we're looking for anything that's purple and orange together, whatever that color turns out to be, and that is our intersection, or the elements common to both intervals. So again, we see that within this area. So let's graph this in more of a final form so it's a little less messy. So our interval contains the number 4, right? That's definitely contained within the purple and is definitely contained within the orange. So 4 is an element of the set. And it looks like we stop at 10. After 10, notice it's just elements unique to set 1. 10's the last number in this, in the purple interval, the purple set. So 10, so the question is, do we include 10? Well, yeah, we do. And it is included within the orange and the purple. So in this case, we have an interesting little picture where the final interval described by the intersection of these two intervals is a closed interval from 4 to 10. So any number, any point between 4 and 10 is included in this interval. So let's write that in interval notation. We have 4 and 10, and the endpoints, both of them in this case, are included. So here we have an interval notation. Again, the interval from 4 to 10, including 4 to 10. Now let's look at the union of a few intervals. We did the intersection, now let's look at the union. In this case, we have our first interval from negative infinity to 0. So everything from the negative infinite direction heading towards 0. Once we get to 0, is 0 included? Yes, it is. So we have a filled in circle for our first interval. Our second interval, again, we'll kind of superimpose these on the same real number line and then take the part that we're talking about and complete it down on this one. So our second interval, our second set of real numbers, is an open interval from 0, okay, same point, oh, interesting, into the infinite direction, or into the positive direction, infinitely far. So we have the orange one looking something like that. All right, kind of a cool little picture. So remember, the union are all the elements in either the first set or the second set, and of course including all elements that are shared. So in other words, all the elements that are colored, that are not this kind of pale seafoam green color on our particular number line, constitute the union of these two sets. So everything moving from the negative direction is purple, so that's included, up to 0, 0 is included, and then everything from 0 not included on this way is also an element of this set. So essentially, is there any point on here that is not part of one of these two sets? No. We have the entire real number line described by the union of these two sets. And that kind of makes sense if we look at what this interval really is. It's basically all of the negative numbers, including 0. This interval is all of the positive numbers. It doesn't include 0, but because of this one that does, and this has all numbers up to 0 but not including 0, our final interval includes everything, because it's everything from here, including 0, and this set says everything right up to the point of 0. So every number, every point is covered in this particular interval. So how can we express that in an interval notation? Well, we could say the interval from negative infinity to infinity. Again, we have to use the correct endings, the parentheses in this case. Or if we're describing this again kind of in sets, we could simply say that it is the real numbers. Kind of a cool little interval, I think. A nice little problem here. So you can probably see how we could describe certain subsets of the real numbers, such as positive integers or different things like that, by using some of these intervals and some of the operations on the sets with them. Let's look at this one. Here we have the union of the set, or the interval, the set from 10 to 14, not including 10 or 14. So let's graph that. So if this is 10, we are not including 10, and this interval goes up to 14. We are not including 14 in the purple. Hello, Sophia. Looks like a little monkey. Our next interval begins at 12, including 12. It goes to 16, not including 16. So again, remember, if we're looking at the intersection, we'd be dealing with the parts that overlap, but in case of the union, we're looking at everything that is purple-orange or purple-orange together. So our final graph starts, the farthest in the negative direction is 10, or purple, so 10, but do we include 10? No, we don't. It's open. All numbers up to 10, or greater than 10, but not 10 itself. So an open circle, color, 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 all the way till we get to 16. And a similar story as with 10, we do not include 16. So another open circle, but all the numbers in between, all the numbers that are included within the purple set, purple interval, and or the orange interval are included in our final interval. So here's a graph describing the union of these two sets. Let's write this in interval notation. Well, we have the interval from 10, not including 10, to 16, not including 16. And let's, for this one, kind of remember, let's kind of draw those circles like we did with the intersections, similar to the Venn diagram. So you can kind of see this as we looked at it pictorially when we were dealing with these, just kind of generally with sets. Remember, an intersection, if we have, or excuse me, not an intersection, a union of two sets would include all of the purple, all of the orange, and everything in between are all included within the union. So here, if this is our purple and this is our orange, the union would consist of all elements and all of that with respect to our number line, again, like we have down here, all the way from 10 to 16, but not including 10 or 16, all numbers up to them. Let's do a few more. Now we have the interval, negative infinity to 20, including 20, but it's the complement. Remember when we talked about the complement of a set? It's all of the elements within the universal set, or all the elements under discussion, in this case the real numbers, that are not in the set that is the original set, in this case negative infinity to 20. So we're looking for the interval that is the real numbers, but not the real numbers in this interval. So this should be a little bit fun, I think. So let's again do kind of what we've been doing. Let's first graph. We'll use our purple. just this interval, but we're looking for the complement of that. Or do you remember how we read this? Prime. So we're looking at this interval prime. So negative 20, or excuse me, negative infinity through 20 is our interval. We are including 20. So we'll fill that in. So this purple is a graphic description of this interval. So all numbers from negative infinity up to 20 and including 20 are included in that. So the complement of this set would be all the real numbers, in this case the green number line, all points on that line, that are not included within the purple interval. So what green section do we have left? Well, every real number extending infinitely in the positive direction from 20 on. Now the question is, do we include 20? Well, no, we don't, because 20 is included within the set. Remember, the complement is all the elements that are not included in the set. So 20 is not in our new interval. So we can graph our interval, the complement of this particular interval, starting at 20, but not including 20. 20 is included here. We are not including it in the complement. All of the numbers moving forward in the positive direction. That looks like something we've seen before. It shouldn't be too hard, I don't think, to write this in interval notation. We can say the interval of 20 to infinity, open. I think we can say that pretty confidently at this point. All right, good job on that one. The complements are kind of fun. We're just going to do one today. Let's look at one more before we leave this. Let's look at another intersection problem. Remember, the intersection, we're dealing with the elements that are common to both sets. So let's move through this like we have been doing. Let's first graph our first interval, our purple interval. It is the interval from negative 5 to 6, including both. Both endpoints are included. This set of numbers represents all the real numbers from negative 5 to 6, including negative 5 and 6. Let's do the orange set, or the second set, from 8 to infinity. If this is 6, 8's kind of close right here. We're not including 8. And we're moving forward positively on towards infinity. Now, this is kind of interesting. I don't think we've seen something like this yet. We're asked to find the intersection, or where they overlap. Is there any point where both the purple interval and the orange interval overlap? No, there's not. And if we drew this like our Venn diagrams, perhaps this picture will be somewhat familiar. Of course, this would be very elongated. This looks like our disjointed sets. Remember, there is no common elements, so therefore there is no intersection consisting of elements. So what is the set consisting of no elements? Right, the empty set, or the null set. Kind of a tricky one, but kind of a fun one, I think. Let's look at just a few more. All right, let's look at these last three problems in which we're dealing with set operations, written a little bit differently in terms of set builder notation. This will be good practice, I think. Here we're letting set E be the set of all elements x such that x is greater than or equal to negative 3. Now remember back to our first few lessons when we were describing sets, and we would say some number is an integer greater than 4, or an integer in between 3 and 10, and we're kind of fuzzy on those endpoints. Do we include 10? Do we include 4? Well, now we can talk about these with a lot more precision, right? We can discuss these knowing exactly if we're including the endpoints or if we're not including the endpoints, and we can do it with a lot less stress on our hand. These symbols that we're involving, writing these sets in set builder notation in terms of inequalities, greatly help both our precision and our shorthand when describing these mathematical phenomena that's going on. So although it takes a little while to get used to reading new things and coming to terms with new notation, new terminology, it certainly proves useful in the end. And this is one very small example of the hard work that we've put in so far, learning how to read this set builder notation, learning how to utilize the set operations, and inequalities and so forth. It really allows us to say quite a lot, quite precise, and quite a limited amount of symbols. Very good stuff, I think. So that's set E. Set F is the set of all elements x such that 0 is less than x is less than or greater than 18. Or in other words, F is the set of all elements x such that x is in between 0 and 18, but not including 0 and including 18. G is the set of all elements x such that x is less than 10. All right, now let's look at our problems. Our first one we're attempting to find a solution to, again graphically and in interval notation, is the union between set E, purple, and set G, orange. And remember, these sets are describing intervals. So let's do our same approach we've been working with the last ones. Let's first graph set interval E. Well, E is the set of all elements x such that x is greater than or equal to -3. So if this is, what color are we? Purple. If this is -3, then x will be greater than this direction of -3, and it goes on infinitely in the positive direction. And do we include -3? Yeah, we sure do, because x is equal to -3 as well. So this is what our purple one looks like. Let's kind of superimpose the G, the set G, on this number line. G is a set of all elements x such that x is less than 10. So if this is 10, x, or in other words, all the elements within G, will be less than 10. Moving in that direction. And we're not including 10 because this is a set of all elements x such that x is less than 10. If it's equal to 10, that's not less than 10. So we're not including 10. This is not describing a set that contains the element 10. So we could say that 10 is not an element of G. All right, we're looking for the union of these two sets. Remember, the union are the elements that are either in set 1 or set 2, and of course that includes the elements that are common to both. So any element, or on this number line, any portion of it colored either orange, purple, or both. Well, that's everything. We've seen this type of picture before. Everywhere from the negative direction and everywhere in the positive direction and everywhere in between are included in one of these two sets. Even 10, which is not included in set G, but it is included in set E. So the union will include 10 on this final interval. So again, our picture for the final interval includes all the real numbers, or geometrically it is the line, extending infinitely far in either direction. All right, let's write this again in interval notation. Well, is the interval extending from -infinity to infinity. And we could also again describe that as the set of all real numbers. So the union of these two intervals is the set of the real numbers, or the interval, all points on the line, the real numbers. All right, very good. Let's look at this next one. Here we're taking set F in yellow, and we're finding the intersection of F and E. So let's graph set F. Set F is the set of all elements x such that x is in between 0 and 18, not including 0, but including 18. So we can write that if this is 0, and if this is 18, set F describes all of the points in between, including 18 because it's less than or equal to, but not including 0 because it is less than. X is greater than 0, not equal to 0. All right, we've already graphed our set E in purple, so no need to reinvent the wheel. We can see that starting at -3, and this number line is clearly not to scale. We include -3, and it extends infinitely far in the positive direction. All right, we're looking for the intersection of these two sets, the elements common to both. So again, that would be the areas that are both yellow and purple on this particular number line. Or if we were again to kind of draw this like our Venn diagrams, there's one set, here's the other. What is included in both? Well, yellow, purple, up to here. So our final graph will look like 18, 0. Are we including 0? Well, 0 is in set E, but 0 is not in set F. So 0 is not included. 18 certainly is. And all of the numbers, all of the elements in between. So this is interesting. The intersection between set F and set E turns out to be set F. So we could say set F is a subset of set E. All the elements in F are also elements in E, but E is not a subset of F, and that makes sense because they are not equal. So let's look at this and kind of make sure that it looks like we're on the right page. If F is all the numbers in between 0 and 18, not including 0 but including 18, and E is all of the numbers greater than -3, well, yeah, that makes sense that F will be a subset of E, as our number line kind of illustrates. Very good work on that one. I thought that one was a little bit challenging. One more. Ooh, we've got an embedded or a double set operation going on here. We have the intersection of the complement of set G and set F. So remember, we're going to first have to find the complement of set G. So set G, we've already graphed, we've already looked at. It is the set of all, or it's the interval from 10 infinitely far in the negative direction, not including 10. So the complement of G would be every other real number, not including what is in set G. So if we were to graph, let's just do the complement of G down here. So we're looking for G prime. So if we were to just graph G, we would have 10, not including 10, working infinitely far in the negative direction. Well, the complement of G will be all of the real numbers, the universal set in this case, not including these numbers. So everything moving this direction from 10, and we will include 10 because 10 was not included in set G. 10 is not an element of set G, remember. So this purple portion here is what the graph will look like for the complement of set G. So we can graph that from, what color are we on? The complement of G. We'll just stick with G as being orange. So if this is 10, the complement of G will include 10 and extend infinitely far in the positive direction. That we got is the complement of G. But we need to take the intersection of the complement of G, or G prime, with F. So again, F we have already graphed. It's the interval between 0 and 18. 0 and 18, not including 0, but including 18. So this is the graph of F. So the intersection between these two are again the overlapping portions, starting at 10 and extending to 18. Now, do we include 10 and do we include 18? Well, yes. 10 is an element of both sets and 18 is an element of both sets. Our picture demonstrates that quite nicely. So our interval for this, kind of running out of room, I'll write it, I guess I'll write it down here. Our interval includes 10, and it goes to 18 and includes 18. So our final picture, well, I kind of did this in reverse back here. So we'll put the final one on top on this one. So our final graph will look like from 10 to 18, including 10, including 18, all the points, all the real numbers in between, and that's exactly what we have described using interval notation below. The interval from 10 to 18, including 10 and 18. Very good work. We're almost there. Last task. You guys have done really good on this. Our job is to look at these intervals and determine the least number within the interval and the greatest number within the interval. And I think it'll help us if we graph these, and possibly you took that same approach on your homework. So let's look at this first interval, the interval from -4 to 13. What is the least number and the greatest number? Well, let's graph it just for practice sake, if nothing else. -4, 13. We have brackets both ways. This is a closed interval. So this interval consists of all the numbers between -4 and 13, including -4 and including 13. So for our purposes of this assignment, we're only interested in two numbers, the least number and the greatest number within the interval. Well, I think this is fairly easy to see. Is there a number in red less than -4? No, our least number then is -4. Not too bad. Our greatest number, similarly, is there a number in red in the interval greater than 13? No, 13, and 13 is included, -4 is included, so our greatest number is 13. Hey, that wasn't too bad. See how we're kind of cooling down at the end of a nice long homework session? We should be able to breeze right through these. Let's check out the next one. Before we graph it, let's see if we can figure out the points. We should if we're comfortable with this notation so far. The least number is 6. There's not a number less than 6, and we're including 6. So the least number in this interval is 6. The greatest number, 28, it's included. Let's graph it just, for practice, if nothing else. So we have 6, we have 28, all of the numbers in between. Is there a number less than 6 and greater than 28? No, we're good. All right, one more. Between 0 and 1, is there a number smaller than 0? No, so 0 is our smallest number. Is there a number greater than 1? No, 1 is our greatest number within the interval. Seeing the endpoints here, they're all included. Let's graph it. 0, 1. The interval consisting of all the real numbers between 0 and 1, including 0 and 1. Nothing less than 0, nothing greater than 1. All right, one more. 0 and 1, let's graph this. It's going to look very similar to this one, right? Except we're not including 0 and we're not including 1, right? So, open circle. Boom, there's our graph. This should be easy. Least number. Wait a tick. All of these were closed intervals. So we had a definite ending and beginning number, right, for each interval, because each interval included both endpoints. This one doesn't. It's all the numbers in between 0 and 1, but not including 0 and not including 1. So all the numbers greater than 0. Okay, so what's the smallest number that's still greater than 0? Well, it'll obviously be a decimal. Is 0.1 the smallest number we could get? Well, I feel like a dime. We can get a penny at least, right? So how would we write that as a decimal? 0.01. Is that the smallest number we could get that's still greater than 0? Well, no, we could venture even farther. 0.001. Is that the smallest number we could get? No. How about 0.0000000 on a million places and then a 1? No, we could always have 1,000,001 places with another 0. Interesting, I think, right? Now we can't have repeating 0 because that is equal to 0. This doesn't include 0. So what's interesting about this, there really is no least number in this interval. We can always find a real number less than any endpoint that we're given. There really is no smallest number within this little interval between 0 and 1. I think that's incredibly interesting. Wow. What about greatest number? Well, we can't be equal to 1. 1's not included. So 0.9 is pretty close, right? 1 more tenth would be 1. But we can get closer. If this is 90 cents, we could get 99 cents. Well, we could do better than that. 3 nines. How about, man, this is kind of looking similar, isn't it? 9, 9, 9, 9, 9, a billion, gazillion, quadrillion, billion, bazillions places down the road. If we stopped, well, we could always get closer to 1 by simply adding another digit, a 9 or an 8 or whatever. So any number, any real number we have getting close to 1, because we're not including 1, we can always find a real number greater than that number, but not quite 1. Well, you may say, well, we've kind of learned notation for this. Why can't we just say the greatest number is 0.9 with this handy-dandy repeated sign? That's signifying 9 goes on forever. Isn't that kind of what we're looking at? Well, yes and no, but remember the problem with 0.9 when we're looking at converting rational numbers. You remember algebraically what happens when we take 0.9 and turn it into a rational number in the form of a over b, where a and b are integers and b is not 0. Remember we showed algebraically that 0.9 repeated is equal to 1. This doesn't include 1. So in a very real sense, at least, in an algebraic sense, we can't include 0.999 on because it is equal to 1. So interesting here, an open interval. Who would have thought that such a little interval between 0 and 1 could cause so much confusion perhaps, or excitement perhaps, or at least something we definitely want to look forward to? Well, this little interval, along with all intervals, has caused quite an excitement in my life as I've studied mathematics. This is quite a fascinating area to delve into. But this is one pretty cool property, I think, that an open interval, in this case 0 to 1, but any open interval on the real number line, there really is no, at least an expressible least number and greatest number. We can always find a real number that is not quite our endpoint, a little bit greater than it. We can always find a number that's a little bit closer to our other endpoint. So there really is no least or greatest number. Kind of tantalizing. I'll leave you to digest that and let that churn. Well, very good job on this homework. We did a lot of kind of repetitious stuff, but this is kind of like learning a skill where it's useful to use both hands, whether it's baseball or basketball or carpentry or whatever. If you can swing a bat with both hands, right and left-handed, you're able to generally do better. Well, we've kind of switched between, we've been saying the same thing, but in really 3 different forms. We've been looking geometrically, graphically, also in terms of inequalities, and also in terms of interval notation. We've been saying the same thing kind of 3 different ways and interchanging between all of those. I hope we had enough practice to go through those, and so we can kind of look at any of those and quickly translate it into any of the other 3 in our minds. But intervals are interesting things, they're fascinating things. I will deal more with them in the future, and I look forward to seeing you as we continue to develop our fundamentals so we can get into some pre-calculus things. I'll see you next time. Have a good day. Bye.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.